Uranus is not only an absolute planetary maverick but also a complete research mystery. No wonder, after all, the shimmering blue ice giant was only visited by Voyager 2 and studied up close, meaning the data available is sparse. Despite this, researchers have succeeded in revealing a number of Uranus's characteristics that are as astonishing as they are confusing. The planet orbits the Sun on its side, its magnetic field has not just 2 but 4 poles, and its surface temperature is an icy -216 degrees Celsius, far colder than it should be. However, astronomers have recently managed to shed more light on Uranus's enigmatic 4-pole magnetic field, which may be linked to a remarkable phenomenon hidden deep inside the planet. The Uranus family has also grown, as experts recently detected a previously unknown moon orbiting the distant ice giant. This discovery increased Uranus's known satellites from 27 to 28. The newly found moon, provisionally named S/2023 U1, is the smallest among Uranus's moons, measuring just 8 kilometers across. Its discovery highlights how much remains to be learned about this peculiar world. However, while identifying new moons is fascinating, the real mysteries of Uranus are far more perplexing and have puzzled astronomers for decades. Since Voyager 2's flyby in 1986, no new probe has visited Uranus, leaving researchers to rely on nearly 40-year-old data to unravel the planet's secrets. If true, this diamond rain could explain why Uranus's magnetic field is so unusual. High pressures and temperatures within the planet could break down hydrocarbons, compressing carbon into diamond crystals. As these diamonds sink, they may carry gas and ice deeper into the planet, generating convection currents that influence the planet's magnetic field. However, a new set of research findings suggests an entirely different explanation. Instead of superionic water or diamond precipitation, the latest theory points to the presence of non-mixable layers deep inside Uranus's interior. This new theory comes from Burkhard Militzer of the University of California, Berkeley, who used high-resolution computer simulations to study the behavior of methane, water ice, and ammonia under Uranus-like conditions. His simulations, conducted at an atomic level of precision, revealed that these elements naturally separate into distinct layers. At the top, there is a conductive layer of water and ammonia about 8,000 kilometers thick, which is partially liquid and hosts the convective currents responsible for Uranus's magnetic field. Below this layer, nitrogen-containing hydrocarbons form another thick zone. These layers remain separated, much like oil and water, preventing vertical flow and altering the way the magnetic field is generated. If correct, this discovery offers a compelling explanation for Uranus's strange multipolar magnetic field. Instead of a complex convective process, the planet's field may be shaped by its distinct internal layering. However, like all theories, this idea requires further testing. Scientists hope to verify it through high-pressure laboratory experiments or, ideally, by sending a dedicated mission to Uranus to study the planet directly. Unfortunately, no such mission is currently in development. While Uranus remains a fascinating target for exploration, no advanced spacecraft program has been approved to visit the planet. One conceptual mission, called iNews, envisions sending 2 probes, one to Uranus and one to Neptune. If realized, this European Space Agency project could launch within the next decade. However, its fate remains uncertain, and with it, the answers to many of Uranus's lingering mysteries. One of the greatest unsolved questions about Uranus is why it is tilted at nearly 90 degrees, unlike any other planet in the solar system. Scientists believe this extreme tilt was caused by a massive impact billions of years ago. A simulation suggests that Uranus may have collided with a protoplanet twice the size of Earth around 4 billion years ago. The impact could have not only knocked Uranus onto its side but also embedded large amounts of ice into its mantle, affecting its heat flow and leading to its abnormally cold temperatures. Despite not being the outermost planet in the solar system, Uranus is the coldest, with temperatures dropping as low as -224 degrees Celsius. The key to this astronomical breakthrough was hidden within the old Voyager 2 data, overlooked until a team led by Jamie Jean Sky from NASA's Jet Propulsion Laboratory reanalyzed it. Their research uncovered that a strong solar storm had occurred shortly before Voyager 2's arrival, compressing Uranus's magnetic field and stripping away surrounding plasma. At the same time, the storm injected high-energy electrons into the radiation belt, giving the planet a temporary, intense electron population. In other words, Voyager 2 had arrived at Uranus at an incredibly rare moment, one that occurs only about 4% of the time. This means that the probe's measurements did not reflect Uranus's normal state but rather an exceptional and highly unusual event. While solving this decades-old plasma mystery marks an important milestone in Uranus research, the ice giant's exotic magnetic field remains an enigma. Magnetic fields on planets typically arise from convection currents in a liquid outer core. Earth, for example, has a typical dipole magnetic field due to the motion of molten iron in its core. However, Uranus lacks the thick convective layer necessary for a stable dipole field. Instead, models suggest that its unusual magnetic structure may be caused by currents confined to a relatively thin outer layer. The interior of Uranus is believed to consist of a solid core surrounded by a mixture of water, ammonia, and methane. This mixture is potentially conductive and could generate a convective magnetodynamo. However, the precise conditions within the planet's lower layers remain unknown, leaving scientists uncertain about what might be obstructing the expected magnetic currents. One hypothesis suggests that water deep within Uranus may exist in a superionic state, where oxygen atoms form a rigid lattice while hydrogen ions move freely, altering magnetic field formation. Another fascinating possibility is that diamonds may be reigning inside Uranus. The immense pressure and temperatures inside the planet could break down hydrocarbons, compressing carbon into diamond crystals. These diamonds would then sink deeper into the planet, dragging gas and ice with them, creating convection currents that influence the magnetic field. If true, this gem-like phenomenon could explain the planet's complex multipolar magnetic field. However, a new set of studies now suggests a completely different explanation for Uranus's magnetic irregularities. A team led by Burkhard Militzer from the University of California, Berkeley, has proposed an alternative theory based on high-resolution computer simulations. These simulations recreated the behavior of methane, water ice, and ammonia under Uranus-like conditions at an atomic level. Surprisingly, the model revealed that water separates from carbon and nitrogen, creating distinct, non-mixable layers inside the planet. At the top, there is a conductive layer of water and ammonia about 8,000 kilometers thick, partially in liquid form. This is where the convective currents responsible for Uranus's magnetic field likely occur. Beneath this lies a separate nitrogen hydrocarbon layer, where hydrogen content decreases with depth, preventing vertical mixing. This separation of materials, similar to oil and water, could be the true cause of Uranus's exotic multipolar magnetic field. While this theory provides a compelling explanation, it still needs to be tested through laboratory experiments under high-pressure conditions or, ideally, via direct exploration of Uranus itself. Unfortunately, no missions to Uranus are currently in advanced stages of development. While concepts exist, such as the European Space Agency's proposed Uranus and Neptune Explorer mission, INEWS, no definitive plans have been made. If approved, such a mission could launch in the next decade, but its realization remains uncertain. One of the biggest unresolved mysteries about Uranus is its extreme axial tilt. Unlike any other planet in the solar system, Uranus is tipped almost 90 degrees on its side. Researchers believe that this dramatic orientation was caused by a massive impact billions of years ago. Simulations suggest that a protoplanet twice the size of Earth could have collided with Uranus around 4 billion years ago, reshaping its orientation. This event may also explain the planet's multipolar magnetic field, as well as its unexpectedly frigid temperatures. Despite not being the outermost planet in the solar system, Uranus is the coldest, with minimum temperatures dropping to -224 degrees Celsius. The colossal impact that tilted the planet may have also trapped vast amounts of ice in its mantle, disrupting heat flow and leaving Uranus much colder than expected. This lingering mystery, along with countless others, can only be definitively answered by future missions to the ice giant. For now, our understanding of Uranus remains largely dependent on the data gathered by Voyager 2 nearly 40 years ago. While new discoveries continue to emerge from reanalyzing this data, many of Uranus's most perplexing mysteries remain unsolved. Until a dedicated mission is launched, the secrets of this enigmatic planet will remain hidden in the depths of our solar system. If you enjoyed this deep dive into the mysteries of Uranus, make sure to like, share, and subscribe to Space Lab for more mind-blowing cosmic discoveries. Rocket Sparkles, stay tuned as we unravel the secrets of the universe, one mystery at a time. See you in the next adventure through space.